So the last talk of this session is going to be presented by Professor David Wood. He's Randy Swift's PhD student. And he actually, something I just found out, he actually also did both bachelor's degree as well as PhD at Berkeley, like some of us, and I think Sharon is one of the very few, and myself as well. So he's a professor in computer science and electrical engineering, electrical and computer engineering at University of Wisconsin-Madison. He co-leads the Wisconsin Multifaceted Project, which focuses on exploring techniques for improving performance and energy efficiency of both homogeneous and heterogeneous multiprocessor servers.
All right, thank you. Everyone can hear me? Yeah, so my primary appointment's in computer science, not in ECE, just keep that straight. So I did my bachelor's here. I actually am pretty sure, with the possible exception of Susan, I have known Randy longer than any of his PhD students, because I was actually hired as an undergraduate programmer on the Ingress project about 2 months before Randy graduated with his PhD. And can't say I really knew him then, but I knew lots of people that he knew, and so when he came back, it was like, oh, I think I know you, and whatever. And so in between, I did my failed startup. I graduated got my bachelor's in '81, did my failed startup, and then came back at the same time that Randy came, and now I'm at Wisconsin, which is, of course, where he started his academic career. So I'm also an architect, unlike anybody else in this room, or at least a hardware architect. So I thought I would try. We'll see whether it's successful or not, but I thought I would try and talk a little bit about the high-level trends in computer architecture and weave them in with where we started with Berkeley Spur and a little bit too much of the weeds of what some of the things I've been doing recently, and then I'll try and pop it back up right at the end. So I worked on the Berkeley Spur project, which Dave Patterson would prefer to call RISC-IV now. And we had some cool technologies. My thesis was on in-cache address translation, and I worked also on the Berkeley Ownership Coherence Protocol, which was one of the first cache-coherent shared memory machines of the day. And I thought, it's been 30 years almost since the chip was made, and certainly 30 years since the project started, and sort of look forward, from there and what's changed. And so I have these slides from a high-level talk that perfectly matches. So the Spur chip was fabricated in a 1.6 micron technology, so just slightly larger than the one that's shown in the bottom left. And then these blue dots are kind of the classic, what did Moore's law give us? How much performance did we get as a result of the technology? And then the red dots are, and how much performance did we actually get from those chips? And so the difference between those has been what has computer architecture been able to give over the last, this is about 25 years since when Spur was built. And so this is pretty interesting, and of course we know that we've seen an incredible growth in computing power since then, and the promise for the 21st century is that we're going to have more personalized health, all these wonderful things with exploiting big data and security and all the things that you guys have all been talking about and going to talk about some more, right? But the question is, will the architecture, will the hardware actually be able to keep up? Are we going to continue to see those gains? Right? And the answer is probably not. So as you've probably heard, Moore's law is ending. The transistor count is still going up, but really we're looking at maybe a couple more generations. Intel is at 14 nanometer right now. 10 nanometer may or may not, probably will happen. 7, they claim will happen. Most people are skeptical. And this is happening largely, one of the other things that is gone is Dennard scaling. So Randy talked about, when he went to this thing at Xerox about, learning about VLSI, what did they teach him? Well, one of the things they taught him was Dennard scaling, also known as the ideal scaling law. And I'm not going to go through everything except, you'll notice that everything decreases by this magic scaling factor alpha. And as a result of that, when you look at the circuit, if you look at the power density, it ends up, everything all cancels out, and you get constant power density. Okay, well, unfortunately, this all hinged around this one scaling of voltage and the scaling of the oxide thickness, and that's basically stopped. You can only go, it's quantum mechanics here. You can only have a finite number of atoms here, and it's like 3. And so a consequence of that is that what we have down at the bottom is no longer that constant power density, but actually the power density is going up quadratically as we scale. Okay, and so that leaves us with some really hard choices. We can build chips with higher power. Oops, ow, burning my phone in my pocket. That's not going to work. We can say we won't make the chips bigger. We'll just make them quadratically smaller and have constant power. That doesn't solve the density problem, but it solves the power to the chip, right? Or we can do something which is called dark silicon, which I'll touch on in just a minute. Okay, which basically means don't turn it all on at the same time. Okay, and oh, by the way, there's other things that are going on here, like these devices don't really work perfectly well all the time, so we have to have a lot more design and redundancy to make, to approximate them as working. Communication cost is increasingly dominating, and one of the fundamental ways that we're going to try to deal with this is through specialization. So this idea of dark silicon is to say, let's make silicon which is customized for the problem that we want to solve. And it may only do that piece, and then we'll run that in an efficient, that efficient circuit for that piece of the computation and turn off everything else. And that has a lot of promise, except that the cost to do this, every unique thing, how are we going to do that? Okay, so that's an unknown question. I'm going to focus. So the real question here is, how does the architecture need to change as this underlying technology falters? Okay, so I'm going to talk about one specific approach, and this is going to be a deep dive into the weeds, where we're going to focus on the communication energy and modest specialization. Okay? So this is some joint work that I've done with AMD. And AMD, as you may know, is one of the leaders in these heterogeneous systems, so gluing together CPUs and GPUs and other pieces. And so one of the key technical questions comes up is, what is the right memory model? If we have all these different disparate pieces, how do we make them communicate together? How do we share memory between them? And so if you reflect back on CPUs, we had this thing called SC for data race free. And that makes it better. And I'll explain what that is in a second. And so, but the hope is that, and this is sort of the executive summary, so I'll go through it quickly here, but the hope is that, well, we could just use this SC for data race free, for GPUs and other heterogeneous things. And the problem is that SC for data race free relies on global communication, on global synchronization, and GPUs use scope synchronization, which I will also explain. We could just say, well, it turns out you could just run slower. But we really don't want to do that, partly because we care about performance, and also because performance and energy efficiency are sort of two sides of the same coin, because you can always turn yourself off when you're done. Okay, so the key technical thing, which I'm going to touch on here, is something called SC, or sequential consistency for heterogeneous race-free, which tries to reclaim performance and still maintain programmer sanity. Right? And if you actually, and this programmer sanity thing, let me just touch on that for just a second, is important because current GPUs are ridiculously complicated to perform. And what is the memory model? It's whatever the hardware does. Right? And that's not really a very attractive solution if you want portable software. So the goal here was to try to specify a memory model that, oops, I'm getting ahead of my slides here, a memory model for these heterogeneous things, for heterogeneous systems. And we actually proposed two. One which was more restrictive, called HRF Direct, which works really well with the kinds of programs that people write on current GPUs. And it has the potential for all the wild and crazy hardware ideas that we have for the future. And another one which is will make it easier to program tomorrow's crazy, irregular programs that people are talking about running and starting to run on GPUs, and works with today's implementation. And when we wrote the paper that this talk is based on, it was like, well, which one of these makes sense, right? And so we put this paper out, and a really interesting impact. I've had lots of papers that had impact, but this one literally we had 2 people who were on the standards committee for for the OpenCL, and they said, "Oh my God, I finally understand this. We have to go change the spec now." And I've never had that kind of immediate reaction. Maybe some of you have, but it was really quite gratifying. So let me just try and not go too far down in the weeds, but I probably will, explain what it is we're trying to do. Okay, so sequential consistency is this really old model. This is what we implemented in the Berkeley Spur processor. I actually was one of the ones who pushed really hard to make that happen. And the goal is to say, when we access shared memory, it should be just the same as if we're operating on a multitasking uniprocessor. So it's really easy to explain and think about. And what happens? Well, it just says that if I have a program, I can look at each instruction independently and go through the thread order here. So on the left, I got thread 1, on the right, thread 2. And I can just think about operating on those one at a time. And a consequence of that is that you can't ever get these weird cycles, right? So in this particular example, we're seeing that thread 1 is storing to A, thread 2 is storing B, and then they're loading each other's, right? And so what that says is you can't get this weird behavior which says that they both got the value, they both saw the initial value 0, okay? And so that's great. It's wonderful. It's easy to reason about. It's kind of hard to build, so you can't have a classical write buffer. So what most systems do is something more relaxed. So if you programmed on x86, you may know that those implement something called total store ordering. If you've programmed on ARM or Power, good luck, I feel for you. Those are much more complicated. Okay, and so in all of those, in all real systems, with very few exceptions, it's possible for x and y to be equal to 0, for this cycle to occur. Okay, and this is really hard to reason about. So, this was identified, back in the late 80s. And in the 90s, Sarita Adve, who was a graduate student at Wisconsin at the time, with Mark Hill, who was another one of Dave's students, who I've worked with very closely over the years since then. And so they basically said, well, what you really, programmers want to reason about SC. These cycles in execution, they're going to make you go crazy. And so that's easy to understand. You want something that's easy to build. And so what SC for DRF says is, well, let's get that sequential consistency for programs that don't have data races. Most people shouldn't write programs with data races, so let's get rid of those. Okay? And so the basic idea is just to say everybody should use synchronization. Here I'm using acquire and release. And we should say, well, if we properly label our accesses to memory, then we can see that there's a release before the acquire, and a release before the acquire, and we'll see that values will always propagate, or so that we're properly synchronized. And so without a synchronous race, we can sort of see that the store to A occurs before the load, and the load down there will also be synchronized and be after the store to A. And so because of that sort of temporal synchronization, we can't have simultaneous accesses, and therefore we should get the behavior that we want. And this turns out that you can do this even when you do, with SC for data race free, you can do almost, not all, but almost all relaxations that hardware architects have ever thought about doing. And so long as you do the synchronization correctly, everything works out great. Skip that. Okay, so that's okay. And so then the C++ memory model. So this was done in 1990. In 2008, C++ was standardized to use a version of sequential consistency for data race free. There's another more complicated model I'm not really going to talk about. But so it basically says, so long as you do your synchronization correctly, everything is going to be wonderful. You don't have to think about the mind-bending things that hardware architects actually do. Okay, so more recently, OpenCL has come out. OpenCL is a language for some of these heterogeneous machines. And what they wanted to do is say, we do SC for DRF. So OpenCL is based on C++. So you'd like to say, SC for DRF. The problem is that these systems are not the same as regular CPUs. Okay, so we need to introduce something that's known as a heterogeneous race, and we need to talk about what that is. Okay, so let's back up a step and say, what is it that we try to do with, what's our shared memory abstraction? Well, of course, the simple shared memory abstraction is, I've got a CPU, I do a store to memory, another CPU, a thread running on another CPU does a load, it gets that value of memory. And of course, the reality is much more complicated. This is what we built in SPUR, was a one-level cache hierarchy, and the Berkeley ownership protocol says, well, it's fine if one CPU does a store, it's going to do the store, it's only going to store into the L1 cache. All right? And the Berkeley ownership protocol says, well, if CPU 1 over here wants to read it, it's got to come all the way around and grab it out of the L1 cache and then bring it back to CPU 1. Okay? And so that's kind of what the whole protocol tries to do. It enforces the single writer, multiple reader invariant so that you can always keep track of things. It enforces this really simple global memory abstraction. Okay? The problem is that when you start to get into scale, and GPUs have thousands and thousands of concurrent threads going on, and they need to communicate with each other. Well, you don't, as I pointed out in my earlier slide, communication is energy, right? And you want to minimize that energy. So if you don't want to spend the energy, don't communicate to everybody in the system. And so what GPUs do is they have an inherent hierarchy and they expose it. So this is actually the programmer abstraction, not the hardware. And so they have this notion of a grid, which can be a 1, 2, or 3-dimensional data structure, which is then partitioned into groups, and then groups are subpartitioned into subgroups, and then each of these individual little squares is what's known as a work item. And the way you program these is from the perspective of that work item, what does that work item do? And so if it needs to access a value from a neighbor, it needs to synchronize with that neighbor. And of course, if we're trying to save communication, most communication is local in physics. And so we want to do most of our synchronization local as well. And so what the languages do is they expose that as a form of scope synchronization. And so this is C++-like. This is actually part of OpenCL 2.0. And you basically say, well, if I'm going to store to a flag, I need to say what the scope is of the store. And there's similar semantics in CUDA, which is another of these data parallel languages. So why do they do this? Well, I gave you the highlight about not wanting to communicate too far. Well, let's make that be more specific. So when we map this onto a cache hierarchy, it looks something like this. And so down at the bottom, we have these little processing elements. Each one is operating on a single work item. And they are communicating up to a cache hierarchy. And there are these write buffers in between. And so there is no read for ownership protocol. We're going to maintain coherence between these caches with flushes and invalidates. And the scope, and doing those flushes and validates have very different costs depending on the scope that we're talking to. So for example, if we are talking to just another work item in our own work group, right? Well, we need to flush our write buffer out to the L1 cache so that the stores that work item 1 did can be seen by work item 2. But if we want to, if we're going to operate between two different work groups, we need to be able to flush those stores not just to the L1 cache, but to the L2 cache, so that the values produced by the orange work items can be visible to the green ones. Okay, so if we go back to SC for DRF, what was the problem? Well, the problem here is we said we have no simultaneous accesses in time, right? But when we put that onto this cache hierarchy, now we are grouping them together into work groups. And so there's not this sort of global, synchronization. So, or to make it be global, what we have to do is these releases here now have to do an L1 cache flush, right? Which is overkill for this case. Because this guy's only communicating with his neighbor. It would be sufficient for him to do just a write buffer flush. But if he's going to get it visible to work group 2, he's got to do a cache flush. Okay. So, well, we could say that's bad. Let's just add scopes to the releases. So when we do the release, we'll say just release work group 1, say release it to my work group. And then in the purple there, say release it at the device level, saying push it out to the L2 by flushing the L1 cache. Okay, here we've saved the performance, but we may have broken the semantics. Because what happens when somebody in the other work group does something different? So in this example here, he's going to read the value that was stored not by this guy, but the value that was stored by him. And does this value, when this guy does a cache flush, does he flush only his stores, or does he flush all of the stores? Does he make all those values visible to work group 1? Okay. We have no simultaneous accesses. SC for DRF says this should all be fine. Okay. But because of these different scopes, will it be fine? Okay. So that's really the question. Okay. This turns out there's 2 answers. One answer is yes, it's a problem. That's the href direct answer. The other answer is no, it's not a problem. And there's trade-offs between these two. Okay. So the question is, href direct is more restrictive. Right? It says if a value is going to be communicated to some other scope, then when you produce it, you have to release it to that scope. And that's quite restrictive, right? Because you may not know. I mean, if you think about software encapsulation, how would you know, right? On the other hand, we know how to build hardware that we might want to build for which, that might be necessary in some of the systems that we are thinking about wanting to build. So the alternative is to say, no, it'll all just magically work. We'll get this sort of transitive flushing property that actually works in most of today's implementations. And it makes it easy to program with, but it really kind of limits you to systems which are hierarchical, which GPUs are. But when you start looking at some of these other accelerators that people are looking at, so compression, encryption, there's a long list of them. They're in your cell phones right now. They don't have a programmable memory model or a portable memory model. Those heterogeneous systems, href direct is not going to work. Well, we suspect will not allow some of those implementations, or at least not make them be as efficient as we might want them to be. Okay, so there was this trade-off, and we, asking the question, which of these should you do, right? Well, really, this ultimately comes down to what do the standards people want it to do, and I cannot stand standard bodies, so I don't participate in those kinds of things. But I think our goal is to sort of identify what are the trade-offs and what choices you have to make. And what has happened is in a very, very short time, OpenCL2 has adopted this. I mean, this paper was published less than 18 months ago. So then, just popping back up a level to sort of the big picture. What are the implications of these technology trends? And I think the answer is, energy, first and foremost, is the fundamental thing. Since the circuits are no longer scaling, we are going to have to try to be much more energy efficient, from the circuits, at the architecture, and in the software. Okay, we need to reduce communication at all levels in the stack, because that's where most of the energy goes. There are various things that we can do in terms of exploiting parallelism to save energy. And I think probably the big question is, how much specialization can we afford to do? What are the abstractions? How do we make systems portable when we don't have general purpose, or when general purpose computing is only one part of the bag of tricks that we have to use to solve computer systems? And there's lots of unanswered questions on what is the way to do this. Do we do this through things that are reconfigurable, where there are inherent energy overheads in doing that reconfiguration? Or if we do full custom silicon, we are locking in a particular design decision that, of course, would require a whole new chip or a new to be able to solve. And these are all unanswered questions. Some of them may be unanswerable. But that's the kind of stuff that I work on. So with that, I will take any questions.
So in the interest of time, so we'll take one question. So I have a quick question. So you mentioned that the standards body is something you don't want to get engaged with, but in your case, the standard body actually adopted your idea for OpenCL. Is that right? How were they able to identify?
Having good co-authors. So.
I see. So your co-authors helped out with engaging the standards body. Which standards body is this?
I don't even know what it is. It's the OpenCL working group. Is it Kronos or something like this? I don't know. I mean, it's part. There's this larger consortium. There's something called the Heterogeneous Systems Foundation and the Heterogeneous Systems Architecture. And this is AMD, Qualcomm, Intel.
So the heavy industry engagement.
It's very much yes. It's all industry basically, and then various consultants and things like me.
Okay, great. Let's thank David again.